I'll start.
Yeah. So today I'm going to be talking about a new technique to generate synthetic data, in particular tabular synthetic data. But first, let me introduce myself. So my name is Vincent Granville. I run my own research lab, mltechniques.com. I was the founder of Data Science Central, which was acquired by TechTarget in 2020. And I'm a scientist with a postdoc from Cambridge University. I work for a number of companies before creating my own startups and research lab. So let's move to the first slide. So a lot of people might be wondering what is synthetic data, what it is used for, or what you can do with it. So I'll briefly explain what it is and the benefit of using synthetic data. Essentially, and I'm going to talk here in the context of tabular synthetic data, as opposed to computer vision problems, sound or LLM and stuff like that. So it's a very specific niche, but there is lots of money involved in there because it's dealing with traditional data like banks, insurance, healthcare, and stuff like that. So essentially, the goal is to try to simulate or create artificial data, in this case, tabular data, that mimics some real data. And there's a number of reasons for doing that. Like I said, it's not just for tabular data. Here I'm going to focus only on tabular data. You can do it for images, video, sound, time series, geospatial data. And usually the company, so there are a number of vendors there, like Mostly.ai is one of them, probably the most well-known, ydata.ai, synthesizer.io, Gretel. These are the companies offering solutions for synthetic data. And typically those who work on tabular data also do time series. And in my case, I also do geospatial data. So why do you want to get synthetic data? There are many different reasons, many different goals. An example is data augmentation. You might have heard the keyword data augmentation. It's when you want to add more data to your training set in order to improve your predictive models. You can also use synthetic data for typical traditional statistical tasks like confidence intervals, for instance. Myself, I use it a lot to benchmark algorithms to get new original data and hopefully some challenging data that is different from what you get in traditional data set or business data sets, to see the limit of the algorithms and get more varied data. Another wide use of synthetic data is to increase some sample size in some data set. Like for instance, a typical example would be fraud detection, where with very few fraudulent transactions. Like for instance, with Visa, when I was working at Visa, with like 4 out of 10,000 transactions were fraudulent. So you don't have much data. I mean, yeah, it's a lot of data because it's Visa's transactions, but proportionally, you have a small proportion of fraudulent data. And so by generating synthetic data, you can increase the size of these samples, which is an alternative to all the balancing and rebalancing techniques that you could use. It's been also used for reducing what's called algorithm bias in some algorithm for imputing missing values. There's also a lot of emphasis on security and privacy. Like for instance, if you want to share your data set contains credit card information, social security numbers, stuff like that, you can use synthetic data to make it kind of impossible to reverse engineer the data set and figure out to preserve the privacy. And also it comes with some security issues. In some other contexts, like clinical trials, it's hard to get a lot of data for some obvious reasons. So using synthetic data is a cheap way to augment your data set. There are different techniques for synthesizing data. Probably one of the oldest, very statistical in nature, is Copula, which is, it reproduces quite well the correlations among the features and the distributions of each feature separately. Agent-based modeling is more related to people doing operation research are going to use this kind of techniques. You might have seen how videos about viruses spreading across the United States, like from east to west. And so that's where agent-based modeling is being used. So there's parametric methods. You probably have heard about Gaussian mixture models. That's one of them. Deep neural networks is the big popular technique used everywhere in generative AI, because actually synthetic data, generation of synthetic data, it's generative AI, it's Gen AI. So typically you have generative adversarial networks, GAN, and there are the techniques as well, and then a bunch of techniques related to GAN, like Wasserstein GAN, which is supposed to work better than GAN or conditional GANs. For time series and geospatial data, you might be using some different techniques. Myself, I've been using multivariate interpolation technique. Then a simple, very simple strategy you would think, which is just adding a little bit of noise in your data, I mean white noise, and then you have some new data that's a little bit different from the original. You could say it's synthetic data. It's kind of the easiest way to do it, but you need to get this noise properly calibrated. And well, I don't think anybody is using that technique seriously. So why did I come with NoGAN, and where does it fit? So when I organized a certification in generative AI, I had a number of participants. We worked a lot on GAN, so the generative adversarial networks, and we faced a lot of issues on some particular data sets, depending on the kind of features involved. We tried to fix it using various ways. We did a lot of improvement. But anyway, in that context, I thought that there might be a better ways to avoid all these drawbacks, like also this convergence issues based on gradient descent. You can get stuck in local minima. So anyway, I came up with this NoGAN. So NoGAN is kind of, there's no SQL versus SQL. So what I want here to convey is the NoGAN versus GAN. And NoGAN does not involve neural networks. So it's actually a lot faster. And the results that you get are more consistent. It's more explainable, more intuitive. So I think it has a lot of potential here. And it's also easier to fine-tune the hyperparameters. You know, if you're working with neural networks, it can take a lot of time to get correct hyperparameters. And when you get a new data set, you might have to come up with a new set of hyperparameters, lots of fine-tuning. And because the training is slow with these neural networks, probably a big selling point here is how much money you're going to save, because when you run this stuff on the cloud, you use your vendors. Eventually it runs on AWS or some platform like that, and they charge money for that. So if it takes a lot of time to run this stuff, you also it costs more money. So one of the main goals here is keeping the same quality, even better, run much faster to save money. That said, this is not just brand new technology that I created yesterday. It's been a couple of months, and I had several participants that helped me and brought actually some data set. to do some testing. So I've been testing on telecom, insurance, healthcare, cybersecurity, education data set. And I even worked with someone who created an open source Python library right now for the evaluation metric to evaluate the quality of the synthetization. This is not just for NoGAN, for any kind of synthetization that's related to tabular data. So you can use that metric. The NoGAN itself, the Python library is just being created. So I need to check and spend some more time on it before sharing with everybody and saying, so it's fine, it's working fine. It's just been released in the last 2-3 days. So I briefly mentioned the evaluation metric. How do you assess whether your synthetization is good or bad? Does it is it mimicking quite well the real data? If it's an exact copy of the real data, it's also of no use. So you need to, so there's kind of a balance between doing a perfect copy of your real data and being too far away from it. But anyway, so there was one particular data set that I created. I call it the circle data set because it's very challenging for a lot of different methods, including GAN. And here, so I tested actually 5 or 6 different vendors, including SDV. SDV is actually a synthetic data vault. It's a open source library for synthetic data. And what is surprising is not necessarily the fact that they are good and bad synthetizations here, is the fact that everybody is rating the synthetization as excellent, wonderful, great. And they're not lying about it. The reason they say that is because they're using evaluation metric that just, they're not great metrics. They compare the univariate distribution, they compare the correlation between any 2 features. So in this data set, all the correlations are 0. There's no correlation. So even in the worst images that you see here, you still get 0 correlation. So they perfectly replicate the fact that there is 0 correlation. They replicate correctly the univariate distribution. So in some way, yeah, it's good. The evaluation metric, they achieve that result. But obviously they are missing the fact that, the circular patterns in the data. So that was the idea, to create a more powerful evaluation metric. I won't have the time to go into the details. So there's a public library for that. I will briefly mention it in a upcoming slide. Yeah, so by contrast, this is what my NoGAN technique did on the circle dataset. I don't want to go too much into the details here because I don't think with the audience might be very technical, but for those who are interested, I try to, at a very high level, explain how the algorithm is working. To summarize, it has some similarities with some similarities with decision trees, with XGBoost, creating a large number of multivariate bins, and creating observation, synthesizing observation in these multivariate bins that I call hyper rectangles. It would be rectangle in 2 dimensions, intervals in 1 dimension, to generate the number of observations in each multivariate bin. Eventually, I'm using a multinomial distributions. I won't go into the detail. People can contact me or read my papers if they want more information. But anyway, in a nutshell, yeah, it's very different from neural networks. And you could say that the creation of the hyper rectangle structure, that's the training part of the model, because once you have that, you can generate as much synthetic data as you want. Here it can get technical as well, so I'm not going to go too much into the technical detail, but why is NoGAN so much faster than neural network-based methods like GAN? In fact, there are a few simple explanations. The training set that you use to create your synthetic data is going to be visited only once, sequentially, one observation at a time. If you run a neural network like GAN, you are going to process the training set is going to be visited time and over. Like, for instance, you might have 10,000 epochs. They call it epochs. An epoch in a neural network consists of processing your whole data set once. So obviously it takes a lot more time. The next points in that slide are a little bit technical, and I don't have that much time left, so I'll be switching to the next slide, which there explain some of the features that make it fast and work quite well. Is that all the categorical features, to make a blend of numerical and categorical feature. Here it's just an extract from some data set. When you have two features, gender, male or female, or region, you have 4 different regions, and I transform these 2 categories into a code. Then there's the inverse transformation, but at the end I get rid of those categorical feature. I'm only going to keep one, which is the code. And based on the way the algorithm is structured, essentially you're going to be processing your numerical features and your categorical features without any difference. They know, and the evaluation matrix is going to be the same. So it simplifies things quite a bit. What I've also done, which I believe everybody should be doing when testing algorithms, cross-validation, well-known machine learning technique to make sure that you're not overfitting and that you're testing your algorithm on future data or on data that's not part of the training set. So essentially, that's what I've been doing here. In this case, a keyword that is usually used is the holdout method. So you have actually I'm going to call it, you have your real data. You split your real data into 2 parts. They're going to be the training set that's used to create the structure, that's used to create the synthetic data, actually. And then there is the validation set, which is the data, the holdout data on which you're going to evaluate your model. So in this case, I split 50-50, 50% for training set, 50% for validation set. And eventually, I will compare the synthetic data with the validation set using an evaluation metric that I briefly talked about, that I call KS for Kolmogorov-Smirnov distance. So what's original here is that this metric, this distance, has been known for quite some time, but here I'm using the full join multivariate Kolmogorov-Smirnov distance, possibly for the first time, and both for categorical and numerical features. So yeah, what I mentioned is that actually this is one of the first piece of code that's been turned into a Python library. The Python library is Gen AI evaluation that you can check on PyPy. So anyway, this document will be shared, so you will have all these are clickable links, everything that's blue there. You can click and find, in this case, the open source library. And here is an example of, rather than using the case distance, so I'm still talking about the evaluation using visual, visualization here, which is scatter plots of 2 features at a time. And here it's one of the data set, was the telecom data set. There was also a categorical feature called churn, which could be either yes or no. Churn in this case meaning that's a customer that abandoned, that left the company, moved to a competitor. And so these scatter plots are for that one particular category, which is churn equal to no. So for customers that are still with that have stayed with the company the whole time. So there are 3 different numerical features here, which is tenure, which means for how many months the customer has been with the company, the monthly charges, and then the total charges. The total charges was a challenging feature for both GAN and for other synthetization method, because it's obviously highly correlated with the monthly charges. So one of the things that I did with GAN, but I've also applied it here, is to use a transformation of those total charges to remove the correlation or reduce the correlation with the monthly charges. And I called it the total charge residues. So in the end, I have these 3 features: tenure, monthly charges, and total charge residues. And you can see that the replication of the distribution, the 2-dimensional distributions, is pretty good. The next slide shows the univariate distributions. So again, you have these 3 features. I believe on top it's the real data, and the bottom is the synthetic data. Like in the previous slide, and I believe the right is the real data, and the left is the synthetic data. While here, I believe the top is the real data and the bottom is the synthetic data. Anyway, it doesn't make a lot of, they're pretty much identical. So if I mixed left and right and bottom and up, it doesn't make much difference. And the evaluation matrix, so the KS multivariate distance, actually a single number between 0 and 1. Let's make it easy to interpret. 0 being a perfect fit, 1 being the worst possible case. So everything is summarized in just one metric, but you can also create a scatter plot like this one, regardless of the number of dimension, whether they're categorical or not, because it's based on the ECDF. Actually, the KS distance is based, the Kolmogorov-Smirnov distance is based on the ECDF, which is the empirical distribution function. It's in Python, it's called ECDF. There is a Python library called ECDF, and actually I added a ECDF library into Python for the multivariate case, because the standard Python library works only in 1 dimension. But anyway, the ECDF takes value between 0 and 1. You have an ECDF both for the validation set and an ECDF for the training set, each taking value between 0 and 1. So you can plot, you can create a scatter plot, and if all the dots are on the main diagonal, that would mean a perfect fit. Now, regarding the hyperparameters, I mentioned that there's some hyperparameters that are more intuitive and easier to fine-tune. Essentially, with the NoGAN technology, one of the first steps you want to do is for each feature to kind of create an histogram to bin or slice the feature in a number of different slices, each one containing about the same number of observations. And the main hyperparameter here is going to be for each feature, how many slices you want per feature. Obviously, if you decide on a large number, you are going to get better results. Usually, you're not going to miss some rare categories, for instance. The drawback of using a very large values is that you can overfit. It might not work as well. It might replicate the training set very well, but not so much. The match with the validation set might not be as good, and then there's some other issues. I don't have the time to discuss about them that are created when you use a large value of these parameters. So in a nutshell, you want to use values that are not too large, but large enough to create something that's good. And so there's some mathematical formulas. I don't have the time to go into that, but it can be automated. Then I also created a little bit different version of NoGAN. So in NoGAN, I mentioned the hyperrectangles, and that we generate the synthetic data, we generate the observations by uniformly distributing, uniformly sampling within each rectangle. But you could change that, use a Gaussian distribution. One of the side effects of a Gaussian distribution is that you can actually get synthetic observations that are outside the hyperrectangle they're supposed to stay within. That creates synthetic data that's is not bound by the range of observation. So one of the problems in many synthesizers, they are unable to produce synthetic data outside the range of observations. So with this Gaussian distributions, you could do that. There's also another way to do it. It's described in my paper and also in the PowerPoint presentation. I don't have the time to explain that in detail. But anyway, if you quickly look at this, you're going to see on the left side, you have the real data. On the middle column is the NoGAN, the initial NoGAN synthetic data. And on the right-hand side, it's the Gaussian NoGAN, which provides some improvement. So I don't have the time here to explain the details about this Gaussian NoGAN. It comes with 2 extra parameters, so there's more fine-tuning that's possible. And like everything else, there's Python code available on my GitHub repository that everybody can use. Like I said, there's going to be a Python, there's already a Python library for NoGAN. I still need to test it further before sharing with everybody. And then there is this Python library for the evaluation metric. So what kind of possible enhancement could I bring to this technology? So before talking about enhancement, one thing that does not need to be enhanced is the fact that categorical features and numerical features are essentially treated the same way after the encoding. So people usually, when computing correlations between categorical features, for instance, they use what's called Cramer's V, which is the equivalent of a correlation coefficient for categorical features. Here, you don't have to worry about that. Data transform work usually help in a lot of circumstances with GAN as well as NoGAN. Sampling outside the range of observations been a challenge for vendors. All the vendors are tested using GAN. Don't do that for whatever reason, I don't know. They might either it's stuck by the algorithm or it could be for business reasons, I don't know. But anyway, there's a way to do it if you want to have more outlier, unusual observations, and one way to do it is quantile extrapolation. I'm working on NoGAN 2 and NoGAN 3, which are very different NoGAN techniques. I will publish about that later. I don't have the time to talk about it here. And one last thing before concluding is that, like in every of my NoGAN synthesizers, it's fully replicable, which is I didn't see any GAN or neural networks that are replicable. Not that it's not impossible to make them replicable, but it seems that people don't care about replicability, and because of that, they're not replicable. You run it twice, you get different results, which with NoGAN, this issue is fixed. It could be fixed with GAN as well. Actually fixed it with GAN. But so that's it. I'd like also to thank a lot of people who worked with me on this project, tested data set, brought some data set, made suggestions, even actually worked with Fabiana Clementi of ydata.ai. And then here you have a few references, the technical papers, 10, 15 pages long, but also you should check my GitHub repository where a lot of the code is can be found. So that's it. Thank you for listening.
Thank you so much. You made a very technical subject easy to comprehend, but I'm sure a lot of it went in one ear, out the other. So I'll have to rewatch and read all of your papers to fully understand everything that you were discussing today. So excuse me if I have some rather basic questions, but in terms of the benefits of this, I would love to know if synthetic data is better in terms of like AI ethics and the compliance side of things for enterprise to adopt this. And another issue that I've seen with generative AI is the issue of hallucinations, which make generative AI, unreliable. You just don't know what it's going to respond, and it's difficult for a user as well to then have to go and fact check and see all of these sorts of things. So I suppose synthetic data you wouldn't actually be able to go out to market. Is that correct with synthetic? Could you build an application on synthetic data, and could it go out to market, or is it just for the initial phases of training the AI model?
No, there's actually here I'm just talking about tabular synthetic data, not computer vision and LLM, generative text or stuff like that, which is a different thing. But yeah, there are clients, and I had some clients contacting me, banks and insurance companies, for instance. And like you said, I think one of the concern with the data that we are dealing with is personalization, ethics, in the sense they're actually even quite focused on that, a lot more than me, who's essentially developing the technological AI. Some of the people are going to bring these other issues like ethics and stuff like that. So to give you an example, and it all boils down to explainable AI, which is related to that. If you are an insurance company and you deny insurance very frequently to Black people, for instance, and your excuse is that, well, the algorithm work well, we're making a lot of money, blah, blah, blah. You end up into, obviously, big problems. That's called algorithmic bias. And synthetic data, one of the goals is trying to reduce this type of bias. One of the simple way to eliminate bias like that is to avoid collecting some features that are strongly associated with race, for instance, or but anyway, that's one of the points of synthetic data, is to reduce this algorithmic bias. Then also the other issue about what you're doing with the data that you collected on people. The synthetic data, if it's done right, you would be unable to find who these people are. And it's not necessarily that easy, because let's think about the insurance data set that I've been dealing with. So there's a guy that is massive expenditure, so really the outlier. You can change his name and everything. You need to be very careful that people are going to figure out, because people are going to be very interested in that case, why this person who costs so much money to the health insurance, so it's going to attract attention. We want to make sure that it's impossible to retrieve, to know who that guy is, because, protection, data protection, security. If people start thinking, well, even with synthetic data, we might figure out who I am, it really creates a big issue of trust and, well, you know what I'm talking about.
And how does can you use synthetic data in tandem with real data and real-time data as well? And how would you identify what's what?
Yeah, it's called augmented data. So what you're doing is blending your training data, so your real data, with artificial data. And if your artificial data is done well, you have a much richer blend of data. So you would be able to get more reliable, robust prediction on future data, because it's been trained on a wider range of data. So the problem with this, though, because you create you have a larger data set with some external data, the accuracy of your predictions might be not as good. It could go down a little bit, and everybody hates that. But on the plus side, you gain robustness. You have something that is likely to work, for much longer, that require less maintenance. The price to pay is possibly, some loss of short-term accuracy. But then again, you can have incredible accuracy on your training set by overfitting, and then once you're outside your training set, it stops working. So that's the drawback.
And is there a business model in creating synthetic data, and so, for example, creating synthetic insurance data and selling it to an insurance company? Is that a business model that you've seen in the past?
Yeah. Yep. So and you have companies like mostly.ai or ydata.ai. That's their business. So they create synthetic data for companies like insurance, or telecom is another example. Healthcare, they have a lot of interest into it as well. And it looks like a strong component of this for these industries is more like privacy, security, when exchanging data with third party. So they are particularly interested in that because of regulations. There is that, algorithm bias, trying to shift to technique, and that's one of the aspects of NoGAN, which are explainable AI, because when you cannot just as an insurance company, you cannot just tell we have an algorithm that works incredibly well. We have no idea why it denies so many people from getting an insurance. We have no idea why Black people, for instance, are penalized, but it works. You just can't say that. So that's why there is an interest into the explainable AI. And here in the synthetic data, I'm focusing on explainable synthetic data, and explainable algorithm. And I believe you guys in Europe, the regulations might even be more strict than in US, even though it's also starting to be, a real concern in US.
Fantastic. Well, thank you so much for your presentation today. I'll stop